Okay, so what you want to do is convert, before you do the derivative, convert all the radicals to exponent form, and then do the power rule, and then you could put back in radical form afterwards. So that could work. And I don't care if you rationalize the denominator. I don't care. You could leave as 1 over root x plus 1 over 2 root x cubed. For 42, find that derivative again. But what you have to do is you have to find the equation of tangent line as well. So that would involve the quotient rule. So you do the quotient rule. Once you get the slope, by plugging 2 and 1 in, well, 2 for x, and then you could write the equation of tangent line because you know it's at 2 comma 1. That makes sense? We're okay with that? All right. For 44, that's just proving that derivative. So if you have a constant, you could do the product rule if you want, but you have a constant 0 regardless. So that's 44. 45, same thing. Just want you to prove that, I think. That's what the instructions were asking. Yep, just proving it. Not that hard. 46 was a little funky. You want me to go over 46 or okay, I'll do it on the board. Yeah. Actually, I'll do it on here because I'm recording this. So what you want to do for 46, yeah, I'll do it off the side because I need some space. So initially you got nRT over v minus nb. So you have nRT over v minus nb. And of course, pressure equals this, right? And there's also another term plus, that was what? An squared, b squared. You're right, it's minus, yes. I'll fix that in a moment. Okay. Okay, that's the original equation, right? So where does v happen? Twice, right? And what I would do is treat each fraction as a separate thing. Like do the quotient rule once and do it again for the other one. So if I do the quotient rule for this, right? What's my top? nRT, right? So remember, low d high. So what's the derivative of nRT with respect to v? Because you're trying to find dp dv, right? If you think about the top of the first fraction, is there any v's up top? So what's the derivative of that? 0. It's a constant. Because there's no b up here. Imagine these are a bunch of numbers. By the way, if you guys don't remember, that's like what, 8 point something or 0.0821. Something like that from gas constant laws. But regardless, it's a number. That's all it is. So that's gonna be 0 times v minus nb. Minus, then leave the top alone. And what's at the bottom, guys, in terms of v? Nope. Just 1. Derivative v minus nb. nb is a constant, and derivative v is just 1 with respect to v. Okay, and then the bottom squared, right? But I'm not done yet because I also have to do the second fraction as well. So minus, let's look at the second fraction. So what's the derivative of an squared? In terms of v, 0, right? Then v squared minus an squared times, what's the derivative of the bottom? Vv over the bottom square, which is v4. Does that make sense? If you clean it up, let me erase this stuff up above now. Now if I clean it up, now I know what's going on. Let's see here. The first fraction, this goes away, right? So you just have negative nRT. And what's the bottom?
NB squared.
Oh yeah, look at that. Okay, that's good. And then you have minus, what's this over here? 0. And that's negative 2an squared b. Negative 2an squared b. And don't you have a v4 on the bottom?
Yeah.
Now clean it up a tad. Doesn't that become minus? And don't those cancel? They become v cubed. And there you go. That's how you got it. Yeah. Just be very methodical. It's incredibly mechanical. Gotta know what your constants are too. That's the key takeaway. Know what your constants are and know what you're taking derivative with respect to what variable. You're doing respect to v. You're not doing a derivative of nRT, right? 'Cause they don't have E in them, so you don't worry about it. So that's what's happening for 46. For 47, hopefully that seems okay. For 47, that's fine. 49 is kind of weird. And Mark, thank you for coming by to talk about that because I was a little confused at first. But I can explain it now. I understand it. But do you guys want me to explain 49? Oh, sure. Okay. Sorry, I glossed over that. Um, you if your position function is 4.9 t squared, that's by the way, like that's free fall. You're looking at like how far something displaces vertically. If you want the velocity, just take the derivative. That's all. Those is 9.8 t, and then do the derivative again to get acceleration. That's all. Okay, for 49. Okay, here's what's happening. If you take this ring here, right? So it looks like a ring in a way. If you were to cut it somewhere along the way, right? Or say you took a piece of paper. Say you took a rectangular piece of paper. I could totally well, I don't feel like doing it right now, but if I cut off a little strip of paper, I could totally fold it and make it circular, right? That's a and of course this paper has thickness. I mean, it's very thin. I totally could do that. And what's the distance of this? If you think about how long is the normal sheet of paper, 11 inches, right? What's the circumference when we make it a circle? Still 11 inches. Exactly. That's what you have to, how you have to look at it. If you were to cut that open, it would unravel like this. So wouldn't this be the circumference? Right, that dimension? Or wouldn't that be or 2 pi r? And wouldn't this be delta r? So what would be my area of that strip of paper? Does that make sense? The area of that strip of paper, right? Now, if you think about it, we're looking at the change in area. Well, what's the change in area here? If I look at delta A, right? Wouldn't that be pi r2 squared minus pi r1 squared? Where r2 is the bigger radius and r1's the lower radius, right? So I kind of see what's happening there as well. So if you think about it, the change in area has to be that strip of paper, right? Because you have the inner circle and the outer circle. Once you take the outer circle minus the inner circle, so that strip of paper is delta A is this. Delta A is actually that. And if you divide both sides by delta R, what do you get? You got delta A over delta R equals 2 pi r. Delta over delta R, if you choose an instantaneous rate of change instead of average rate of change, there you go. dA over dr equals 2 pi r. So that's how you would reason it. So if that makes sense. And by the way, I mean, this race could change as you're expanding, right? So sure, whatever the race is at that moment, but that's the way you could think about it. So it's more of a thinking question. I think it's not a test question. Don't worry about it. 56, just do the derivative twice. Once and twice. There you go. Not hard. Looks like that's a multiple choice question. Yep. That's super easy. And then D. D.
I got D.
D's and dog.
I read them.
Okay. And then what else we got? We got 1, 2, 5, 8, 9, 19, I think. So number one, that's that the linear motion stuff, that's pretty easy. Yeah, that's not hard. Hope you guys are okay with that. And these answers I think aren't schooled you, right? Yeah, okay, good. 2, more of the same stuff again. Pretty straightforward, it should be, hopefully. 5, I think I just told you to draw secant lines for some of these. That's also should be pretty simple. 5's asking the plots, the points, work it out. Find the velocity at certain places, which is by doing that looks like average. Yeah, you're doing average rates of change, but you're doing a symmetric difference quotient. So for V of 1, you use 1.5 and 0.5. We talked about that. For V of 2.5, you go between 2 and 3, 3.5, 3 and 4. 8, what's 8 about? Yeah. If you're ever being asked like, here's the quantity, you want to know how fast something's changing. So we do have a quiz today. Quiz is just it's a derivatives quiz. It's pretty straightforward. It's using stuff that we've talked about already, like product rule, quotient rule, graphs of derivatives. So it'll be fine. You guys will be fine on. But I do need to kind of just see how. And again, it's a quiz. I'll go.
Is the quotient rule gonna like be shown?
No, you need to know that.
Okay.
Yeah, you need to know that. Remember, low D high,
Yeah, I think
minus
I
high D
remember. I
low.
was just
Okay,
wondering.
okay, all right, good. But this one here, there's a quiz question kind of like this. It's not hard. If you're given the quantity, you want to find the rate. What do you do? What do you do with the quantity to get the rate? You take the derivative. What's the derivative of that? Actually, the one I have is much easier. This is a little, but you could actually, yeah, actually, you do have to distribute. You have to do 30 minus t times 30 minus t. But again, it's not hard to do. But trust me, I will give you one that's much easier. This is a little more challenging. But notice how those expanded first, and then we did driv afterwards. But I know you guys can FOIL. I'm not worried about that. But the one I have in the quiz, I have right here. Yeah, it's way easy on the quiz. It's way easy. You don't have to expand anything. And just plug in 10. That's all. And if they ask for the average rate of flow, whatever, just do that. And then what's the one more question? I think it was number 9. 919, I think. Wait, how many questions did I ask here?
A lot.
Too many, huh? 919, I think that was it. Okay. For 9, yeah, that's just what we talked about on Friday. Any questions on 9 you want to talk about? Breaking this. This is not on the quiz, by the way. I'm not doing this on the quiz. So I'm not doing that. No questions? You're okay with that? Reading the velocity graph correctly. Okay. Then finally 19. More of the same thing. But here you have an equation instead of a graph or a table. And just do the derivative once and twice to get all those things. Any questions on 19 at all? No? No? Okay. All right. Then I think we're okay. Perfect. Okay. Yeah, so we got what time at 30? So I'd say around 11:50. I don't need too much time to yeah. Yeah, so yeah, about 11:15 we'll do the quiz. Yeah. All right, so here's what we'll do. Let's jump to derivative trig functions first. So let's go to 3.5 because I really want to make sure you guys know this. I'm okay foregoing the previous page if we have to. Because I've done that before. Because I can always make it up later. But let's talk about derivative trig functions because I think that's important. And this should be pretty fast. So let's go to 3.5. Okay, here we go. So if we consider the graphs of sine and cosine, so what's y equals sine x look like? We know this, right? It looks like this. But if I did d dx of sine x, if I put this in the graphing calculator, if you think about it, or actually I won't do the graph calc because I know how it looks. But you can. I trust you guys can. But just think about it. If we're at x equals 0, is your tangent line positive or negative?
Positive.
And as I get closer to pi over 2, the tangent line is still positive, but when I get to pi over 2, it gets 0, right? So what happens between pi over 2 and pi? The tangent lines are now negative. And it's probably the most negative at pi. But then it starts getting less negative until we get down to
0.
3 pi over 2. Exactly. So the graph is actually going to look like this. If you were to graph it, by the way, this goes to 2 pi. That's the period, right? We know this.
What's the maximum?
1 and -1. Yeah. So 1 and -1.
Oh, no. Sorry, not per amplitude. The maximum slope of the tangent line.
Oh, that's going to be 1 or -1. And you'll see why. So the graph looks like this. So what does that graph look like to you? So it actually is cosine x. The derivative sign is cosine x. Yeah. All good.
What's the line x equals x for the derivative sign?
Oh, that's when you plug in the calculator. This is for the TI-84 calculator. If you want to see how it looks. But I don't want to do that. So yeah, if you wanted to use the TI 84 calculator, you would type that in. Right. Okay. If I do it for cosine, okay, let's go backwards now. If you look at cosine,
Starts at 0.
it starts at 0, but then it's negative slopes.
So it's negative sign off.
And then it comes back to 0, then positive. So if you did it the other way around, if I graph d dx of cosine x, it's actually gonna look like this. So that'll be negative sine x. One way I remembered, I didn't really understand this graphically in high school because I was kind of a space cadet at times. So I didn't really pay attention. That's my fault. You guys are much more focused, so I appreciate that. Thank you. But the point I'm trying to make is that I had a way of memorizing it. The way I memorized it was derivative of cosine, because cosine comes for sine in the alphabet. So the derivative of that would be negative sign. I'm not sure that makes any sense. I don't know. Well, no, because there's also something called no, because there's also called integral that you do later on in the second semester of calculus, and the integral of sine is negative cosine, and then it goes the other way around when you do the antiderivative. That's how I remembered it. So cosine for sine the alphabet derivative, that's negative. I don't know if that makes sense, but anyway, it is what it is. Oh, very important. You got to be in rating mode, guys. There's no place for degree mode here. So if you do have some calculator work with this stuff, if you graph it actually, you gotta be in rating mode. If you're in degree mode, it's gonna be a really weird answer. There's a reason why it is. It's based upon the derivation. If you actually go through the formal proof of proving these, you have to assume radians as you go through the formal proof. That's the reason why. Yeah.
Find like a random question.
I love random questions. Good.
For radians,
Mhm.
what does 2 pi actually mean something, or is it just something picked by whoever invented?
No. There's a reason for it. If you actually do proportional reasoning, that's well, Mr. Van should have taught that to you. Well, I'm sure he did, but if you go around the circle once, that's 2 pi r. If you compare it to an arc, so a radian is defined as when the arc is the same length as the radius.
Okay.
So if you compare r, so the arc is, we'll call it arc r because the same length as the radius. If you compare that to 2 pi r and compare one radian 360 degrees and cross multiply, you get 360 equals 2 pi. If you go through the actual proportional reasoning bit of it.
So for radians, the arc equals the radius.
One radian is defined as the central angle of a circle would equal 1 radian if its arc it intercepts, if that length of the arc equals the radius of the circle itself. Yeah, that's where it comes from. So it's a formal definition, and then yeah, sure, someone probably made that up, but then that's the relationship based upon that connection. So okay, we know tan, sine, or cosine, right? So what rule am I going to use here? Quotient rule, right? So if I do this, you should do low d high. So cos x, and what's the derivative sign again? Cos x minus high d low. What's that going to be? Negative sine x. Yeah, it'll be one up top and over the bottom squared. So what do you get up top? Cosine squared x plus sine squared x. Good. And you're using your identities. That's lovely. By the way, please never do this. Why is that bad? Yeah, it's a plus sign. Please never ever do that. If you really want to get on my nerves, you do that. Don't do that, please. I know you guys have earned that. PEMDAS, right? Please don't do that.
Get some people in your algebra too.
Yes, I'm about to drop the F-bomb. Yeah, I swear sometimes when I grade this stuff at home and I have little kids, so I was like, what are you doing? Like I want to go back to middle school teaching and yell at their middle school math teacher. Like, what did you not teach these kids properly? Anyway, I'll stop. You see, I got secant squared x, right? Because because you have one up top, 1 over cosine squared secant squared x. So derivative tangent is always secant squared x. Yep.
Did you Oh, wait, never mind. You have to use number.
No worries. And by the way, this does make sense, right? Because if you think about tangent, how's tangent look? Bunch of those. Are those derivatives ever negative? They're always positive, right? And if you're squaring something, that's always supposed to be positive. And by the way, secants can't be really any number, right? Because what's the range of secants? Between -1, sorry, -1 and 1 to infinity. So this makes sense. This will make sense. Just to show you how we got. I'm not going to go through the formal proofs of these, but they're pretty similar. This will be negative cosecant squared x. This will be secant x tan x. And I'll be honest with you, I have these memorized. If I don't teach this stuff for more than a year, I actually forget.
Why is it not negative secant squared x?
Because of my derivation.
Because if you have 1 over cos, isn't that gonna be -1 over cosine squared x for secant for derivative of secant x?
No, because when you secant you're doing one of cosine, but then when you go through the quotient rule, it should come out to be positive. Yeah, if you go through the motions, it will actually. So want to make sure we're clear on this. That's secant x times tan x, negative cosecant x times cotan x, and that's negative cosecant squared x. Oh yeah, so you have sine over cosine. So you do low d high. So low is cosine times the high. Derivative of sine is cosine. Then you do the other way around. Sine times derivative of cosine, which is derivative of cosine is negative sine. They go away because you're doing negative minus a negative, right? So you get cosine squared plus sine squared. By the way, don't worry about double angle, some difference formulas. That has no place in AP calculus. Don't worry about that. I highly doubt you'll, unless the college wants to change things eventually, but I don't think that's anything to worry about. By the way, again, secant is 1 over cosine, cosecant 1 over sine. One thing I think you guys will find helpful, I think I shared this with you guys a while ago. Let's see if I got it here. Yeah, here we go. This will actually now make more sense to you guys. I think I did show this to you guys. And actually, I think I'll print it right now. It's a little cheat sheet. I mean, you can't use it on a test, but just to help you study, like, hey, formal definition of the derivative, the alternative definition, derivative constant. If you have a constant multiple, some difference rule, power rule, product rule, quotient rule. We'll do chain rule. Actually, there's gonna be a video on chain rule on Thursday. I won't be here. Mr. Lau. Actually, no, Mrs. Sue will be your sub. And she'll you guys watch a video on chain rule, and then she'll help you if you guys are stuck. But you have that. All the trig stuff's right here. We don't do inverse trig. We don't do these other ones, but I'll print this for you guys. So you have this as a reference. I'll print school too. Yeah, 100%. Yeah. So anyway, let's go back to notes again. Okay, so let's actually do this. Let's do some problems with this stuff. So if I think about it, I'm doing the derivative of y, right? So y prime, the first bit, what rule am I using for the first part? What rule? X times sine x? Product rule, good, okay. X times cos x. Then I'll switch colors for a bit of contrast. And then what's the derivative of cosine x? Okay, do things go away here? Yep. What are you stuck with? X cos x, there we go. And we talked about how you can verify it. You can always go to the graph calculator, graph the original equation, then graph its derivative, and then graph the derivative got by hand, and they should be the same thing. So you can totally just check your work that way. Question on example 1. Now, example 2, if we want to find normal line, what does that mean, normal? To the tangent line, right? So let's find the slope first. So that's going to be perpendicular. Actually, I was a little confused why I wrote that. So what's the derivative of cotangent again? It was negative. Okay. You do need to know your unit circle pretty well now. At this point, like, it can't be, it's got to be very comfortable with this. So if you think about it, you're really just doing this here. if it helps, you could do that. You know cosine is 1 over sine. You're plugging pi over 4, you're squaring. Do you guys remember sine pi over 4?
Over two.
Yeah, good. So that's -1 over √2 over 2 squared. What happens if I square √2 over 2?
Just 2/4.
Or 2/4. Yep. So you get -1, which should be -2, I think. Yeah.
And the normal.
Okay.
2. Or no, 1.
So the perpendicular, so the slope will be 1/2, the perpendicular slope. And if I want to write the tangent line, I do y minus 1/2 x minus pi over 4. What's the cotangent pi over 4? You guys remember that? 1. Yep. Remember, cotangent of pi over 4. And that'll be your y1 in the slope, in the point slope form. So that should be pretty straightforward. Very mechanical again. Take the derivative, use unit circle knowledge, get your slope. But it's normal, so do negative reciprocal, and then do point slope form. And in order to get the y coordinate that goes with x equals pi over 4, plug it back in the original equation, using unit circle knowledge again to get that. Yeah, okay?
Yep.
All right. Okay, why don't you guys try example 3 on your own? And then yeah, I guess we could do the proof. We'll have time for it. Okay.
We have to memorize all these fantastic where we have like a terms like license.
You gotta memorize them.
What's the derivative and and then times. Then we have this. Let's do it first. So as you can see, those two things on.
Okay, so far, low, D high, low, D high, minus high, D low, or low squared. Okay.
Wait, why is the derivative of 1 minus sine x negative?
What's derivative of 1?
Oh.
Yep. And what's derivative of sine x? Yep. Be really careful with the negatives though, because that can mess you up big time.
I don't know what the whole. One.
What do you up top? Okay, and leave it like that. You don't need to expand the bottom. It does nothing for you. If you want, go ahead. But if you mess it up, I'll take out points. So just don't do it. Why shoot yourself in the foot? Doesn't make sense. Just leave it alone. It's all good.
Where'd you get the 1 from?
Oh, I made a mistake, guys. Crap. Ah. You see the mistake I made? Okay, thank you. I would have checked my work, by the way, and graphed it. I made a mistake. What mistake did I make?
Should be negative.
Should be negative.
Yeah, it should be negative sine x. Yeah, my apologies. It happens. Good, you guys paying attention. That's negative sine x. Oh, this does actually factor out nicely. Okay. Or simplify nice. Okay. So what does the top become now? My apologies. All right. Yeah, look at that now. Now this is lovely. Can I simplify further?
Yeah, you can take out one of the sums for
So in that case, I would simplify. And I would have known to check my work by graphing the original, graphing the derivative by doing d dx of the original x equals x, and then graphing what I got by hand. If they don't trace each other, then of course I made a mistake somewhere. So the importance of checking your work. So yeah. And I'm human. I forgot to do something. Yeah. So that's my fault. So okay, we're okay with that?
Mhm.
All right. before we do the formal the proofs, I do want to kind of go back because I kind of do like these problems back at the end of 3-4. Let's go backwards a little bit. Sorry, guys. If we go over here. Oh, yeah, Ethan, go ahead.
I know, like D over dy. Sorry, D over dy.
When you do what, sorry? Yeah, on the left side, yeah, of course. Or you could do y prime. Yeah, you could y prime is fine. All right, let's take a look at this one here. So we're going backwards. Sorry, guys. We're going back to 3-4. I kind of care about this problem. So do you want W prime at 12? I think we talked about this already. If you think about it, you don't have the equation for W. W is the temperature of water in a pond. But you told us differentiable, right? If you told us differentiable, you can assume continuity. You can assume that, right? And so if you think about it, if this were like 3, 6, 9, 12, 15, and say I did a curve for this, right? And I want the so W prime at 12, wouldn't that be the tangent line at 12, right? So if I drew a tangent line here, it would look like this, right? Well, how can I approximate that? What can I do to approximate it? Yeah, because what if I did the secant line? Yeah, we already talked about this, I know. But if you think about it, W prime 12 can be thought of like this. W15 minus W9. You see how the blue and brown lines would be pretty good, pretty close in slope, right? It's a good approximation.
Yeah.
And you're totally an approximation, so fine. So W15 is what? 21. W9 is 24. Bottom is 6. So what do you get as your slope? Yep. And so it'd be negative 1/2 degrees Celsius per day. So at the moment, we're on the 12th day, the temperature is dropping about 1/2 a degree. It seems like it's dropping by about 1/2 a degree. You could look like that. So do we need a graph? No. Just nice to have, but you know, we understand what we're trying to do. We're trying to do a symmetric difference quotient. Wrong, good. Yeah. Let's interpret. Yeah, it's good.
12 days. It's reduced.
Yeah.
By -1.
Yep. On the 12th day, the temperature of the water. I know they didn't ask for it, but it's good to do. Of the water in the pond is dropping by
Average.
0.5 degrees. Yeah, you could that could work.
You say like
Yeah.
on an average or
It's not really an average necessarily. It's because it's at an instant.
but like we're
At the instant of the t equals 12. So it's not really an average. Yes, you did do an average rate change to approximate it.
because isn't that kind of like the average between 9 and 15?
Right, but we're interpreting W prime though, which is an instantaneous rate of change.
So if the conditions of.
Right.
We say like about 0.5 degrees Celsius. It's not really.
That's a good question. I don't know that. No.
Well, if it's an approximation.
But you gotta tell me what the value split with the units and of course the time is happening.
So it's like, if the
Mhm.
conditions of the 12th day were replicated, it would just be a 1/2 degree.
Correct. Correct.
So like when I thought that was literally like the way you find the average was by doing
Yeah, we're using that to help us approximate. If I had an equation, I would not do an average rate of change, and I'd actually do the derivative and
Right,
find.
but like how do you find the average rate of change?
Yeah, you take the average rate of change by finding the slope between 2 points, and you're using that to approximate the derivative. But what is the true meaning of the derivative, though? It's an instantaneous rate of change.
Yeah.
So you have to be present to that.
Aren't we approximating here?
Yeah, we're always
Yeah, we're
approximating.
approximating
Yeah.
E and-
We're always approximating. So same thing here again. You want to do R of 50 minus R of 40 over 50 minus 40. And that will equal that will roughly equal, it's an approximation, mind you, R prime 45. So you work it out. That's not hard. That's 55 minus 40 over 10, which would be about 1.5. That's gallons per minute squared, guys. Because you're looking at how the flow rate is changing with time. Because right now R represents gallons per minute. It's a rate of fuel consumption. So it's almost like an acceleration for liquids
So if you were to take that derivative, it would be gallons per minute cubed.
squared.
No, if you were to take the.
Oh, again, sure. If you did it again, sure, right. It's kind of like just how the rate's changing. If the rate's increasing or decreasing. It's kind of like if you like have a garden hose and then you slowly kind of let the nozzle loosen it, and more water comes out. Yeah,
Where's the
right. Or like you turn on the faucet and keep turning it on, and more water starts coming out. So, all right.
Oh, yeah. Oh, yeah.
I think I understood time, and I think I accomplished what I wanted to. We'll forego this formal proof. I can do another time. It's not a big deal. It's not on the test. Don't worry about it. You guys know your unit circle?
Of course.
Okay, we don't worry about it. Okay, I think we're good. I got what I wanted to.
Mr. Band taught us one thing. Can I borrow this?
Sure, of course.
We got the unit circle down, Mr. Band.
Is this another